suppose we have the following sets of functions. First, b1 is going to be equal to 1 e to the minus ix, e to the ix. b2 is going to be equal to 1 square root of 2 cosine x, square root of 2 sine x. We want to show that b1 and b2 form orthonormal sets with respect to the following inner product. Now, if I have two functions f and g, we define their inner product by 1 over 2 pi times the definite integral from 0 to 2 pi f of x times the complex conjugate of gx dx. Once we verify the orthonormal set property, we want to verify Parseval's identity for the function f of x equal to sine x. Okay, before we compute anything, what's our motivation here? We're trying to set up an analog for function spaces to finite dimensional vector spaces. So, if we take the set of polynomials, if I take two polynomials, add them together, I get another polynomial. If I take a polynomial, multiply it by a scalar, I get another polynomial. So polynomials are going to have properties of vectors. Now, in general, we're going to want to push that one step further. So the idea is going to be, okay, if you're in linear algebra, it's an inner product. If you're in multivariable calculus, it's the dot product. We're going to want a notion of the length of a function. So it's going to be the analog of length of a vector or inner product. The models for our function spaces are going to be based on the picture for R3. There, we have an orthonormal basis given by the standard unit vectors. So we have E1, E2, E3, and then the picture looks like this in R3. Now, orthonormal basis has three parts. First, orthogonal. If I take EI, EJ, where I is not equal to j, take the inner product, we get 0. So our vectors are mutually orthogonal or mutually perpendicular. Then we have normalized. That just means each vector has length equal to 1. So if I take the inner product of EI with itself, I get a 1. Okay, these vectors are all unit vectors. And then basis. So basis is just going to mean if I take any vector in R3, I can write it as a linear combination of E1, E2, and E3. Now, if I have V equals C1, C2, and C3, we just write it as the sum C1, E1 plus C2, E2 plus C3, E3. With that linear combination and the orthonormal basis, we get two formulas. First, I'll have CI equals V inner product with EI. So if you want to pick off any coefficient before an EI, just take the inner product with EI. Then, for the length squared, we just take the sum of the square of the C's. Now, in R3, this is just Pythagorean theorem, but when we go to function spaces, we call it Parseval's identity. Okay, there's nothing special about using the standard unit vectors here. All we need is an orthonormal basis. So, let's take a look at what happens if I use the vector square root of 2, square root of 2, 3. Now, if I take its length squared, we're going to get square root of 2 squared plus square root of 2 squared plus 3 squared. It's going to give me 13. Let's see what happens if we go to another orthonormal basis. So I'll use F1, F2, and F3, where F1 is 1 over square root of 2, 1, 1, 0. F2 is going to be 1 over square root of 2, 1 minus 1, 0. And then F3 is 0, 0, 1. So you should check that that's an orthonormal basis. Once you do that, we can look for the C's. Now, C1 prime, we take V against F1, and we get a 2. For C2 prime, I take V against F2, I get a 0. And then for C3 prime, we take V against F3, and we get a 3. We can get two pieces of information from that. First, V is equal to 2F1 plus 0F2 plus 3F3. So, the C's let us write V as a linear combination of our F's. Then we have the formula for length squared. That's going to be 2 squared plus 0 squared plus 3 squared, and that's going to give me a 13, and that's going to match what we got when we used the standard unit vectors. We want to replicate the results on R3 for our function spaces. Now, let's start with B2. In this case, our functions take real numbers, return real values. So if you want to just consider things over R, that's just fine. Okay, the difference is how you take your linear combinations. So if we're over R, A1, A2, and A3 are going to be real numbers. If you would take linear combinations over C, these three will be complex numbers. Okay, all the work that I do will be unchanged. Now, when we have this span, I want to show that our set forms an orthonormal set, and then we'll have an orthonormal basis for the span here. Okay, so first we need to show orthogonal. So that's going to mean if we take any two of our functions, put them in our inner product, 0 comes out. So let's check that. So if we do 1 against square root of 2 cosine x, okay, we just push through the definition. We'll be left with any derivative of cosine x, which is minus sine x. And then if I put 2 pi and 0 in there, zeros come out. So our answer is 0. For 1 against square root of 2 sine x, same idea. We're going to take any derivative of sine. It's going to give me cosine. We put 2 pi and 0 in. 1 comes out for both answers, get a 0. Then if we try square root of 2 cosine x against square root of 2 sine x, okay, we're left with any derivative of cosine x sine x. We can do a u substitution. So I'll let u be equal to sine x. You work it out. They're winding up with 1/2 sine squared of x evaluated at 2 pi and 0. But sine of 2 pi and 0, going to give us 0. So again, 0 comes out. So our three functions are going to be mutually orthogonal. Okay, next I have to show unit. So we want to show if I take any of these functions, put them in the inner product with itself, we get a 1. Now, if I put 1 in with itself, okay, it's a straight shot, you're just going to integrate dx. So you get x, put in 2 pi and 0, 2 pi comes out, and then we're dividing by 2 pi, so I get a 1. If we put square root of cosine x in against itself, you're going to be taking the antiderivative of cosine squared. So for that, I'm going to use the double angle identity for cosine. Okay, we'll use that as cosine of 2x equals 2 cosine squared x minus 1. And then we solve for cosine squared x. That's going to give us 1/2 plus 1/2 cosine 2x. And then any derivative of that, straight shot. So we'll get a 1/2 x. And then here that's going to go to sine of 2x, and we divide by 2. Okay, anyway, for the second term, when we put 2 pi and 0 in, that goes to 0. So the only thing that'll be left is the 1/2 2 pi. Now, when we take a look at what happens there, we're just going to have 2 over 2 pi times 2 pi over 2. So we're going to get a 1. So this function is going to be a unit vector. Same exact method is going to show that square root of 2 sine of x is a unit vector. The only change is going to be when we get to using the double angle formula for cosine, you're going to switch to 1 minus 2 sine squared x, which is just going to change this plus here to a minus sign. Okay, then when you work that out, this is a unit vector also. Okay, what do we get from this computation? Well, I want Parseval's identity for sine of x. So the first step is writing sine of x as a linear combination in terms of B2. So that's going to give me 0 times 1 plus 0 times square root of 2 cosine of x plus 1 over square root of 2 times square root of 2 sine of x. Then with this, we just take the sum of the squares of the c's. So it's going to be 0 squared plus 0 squared plus 1 over square root of 2 squared. That's going to give me that the length of sine of x squared is equal to 1/2. Let's move on to B1. We have 1 e to the minus ix, e to the ix. These functions take real values, return complex numbers. Now, if we're talking about vector spaces, we're going to want to be over the complex numbers then. We want to show that these functions form an orthonormal basis for their span. So that's going to be all linear combinations, C1 plus C2 e to the minus ix plus C3 e to the ix, where C1, C2, and C3 are complex numbers. Before we do any computations, let's first do a little bit of review. First, the complex numbers. Main result we're going to use, Euler's formula. That states e to the ix equals cosine x plus I sine x. What we're doing here, we're taking e to the ix, breaking it into its real and imaginary parts. Now, if we fix an x, what we're doing here is, okay, if I consider the complex plane, the x-axis is the real axis, the y-axis is the imaginary axis, we're going to take e to the ix and identify it with a point in the unit circle. In fact, it's going to be the point that goes with the angle x. In rectangular, that point's going to be cosine x, sine x. What happens if we take the complex conjugate of e to the ix? Okay, well, complex conjugation is going to take the imaginary part and then multiply it by a minus 1. So we're going to get cosine x minus I sine x. Sine is an odd function, so we can move that minus sign to the inside. And then cosine's an even function, so I can replace cosine of x with cosine of minus x. Then we note, by Euler's formula, this is just going to be e to the minus ix. So all we're doing here is taking Euler's formula. Wherever I have an x, we now have a minus x. So that's our rule for conjugation for e to the ix. Now, there's going to be two identities that I want to use when we do our computations. So the first one's going to be e to the ix times e to the minus ix. It's going to give me 1. One way to see that, if you add the exponents, you get a 0, and then e to the 0 is 1. Another way is to pull out Euler's formula. So there we'll have cosine x plus I sine x. For e to the minus ix, here we see we have cosine x minus I sine x. Then when I multiply these, we have a difference of 2 squares. So I'm going to have cosine squared minus I squared sine squared. But I squared is equal to minus 1, so I have cosine squared plus sine squared. And that gives me a 1. So that checks. Then we'll want e to the ix times e to the ix gives me e to the 2ix. And then by Euler's formula, that becomes cosine of 2x plus I sine of 2x. All right, to get that, we could just square cosine x plus I sine x. And then what happens? The real part will be cosine squared plus I squared sine squared, or cosine squared minus sine squared. That's going to be equal to cosine of 2x. So that's our real part. Then for the imaginary part, the part with the I, we have 2 cosine x sine x, and that's just going to be sine of 2x. So we get cosine 2x plus I sine 2x as desired. Now, integrating with complex numbers. Okay, so suppose I have a function f that takes real numbers, returns complex values. First, we could think of our capital F as being broken down into its real and imaginary parts. So that's just going to mean we'll have functions little f and little g that take real numbers, return real numbers. So what's going to happen is, okay, the real part does exactly what you think it would, but on the imaginary part, it's just going to collect whatever capital F is doing with the I. Then, if we want to integrate capital F, it does exactly what you think it would do. You're just going to take integral of your little f, integral of your g, see what comes out there, and then recombine things at the end by just putting your I back with the g. Okay, so that's how I do integration with complex values. Let's take a look at our orthonormal set. All right, we have 6 things we want to show. First, we take 1 against e to the minus ix. Now, we conjugate the function in the second slot, so e to the minus ix becomes e to the ix. So we're really just integrating cosine x plus I sine x. By my rule here, we break that up into 2 integrals. Okay, but if I integrate cosine from 0 to 2 pi, I get 0. If I integrate sine from 0 to 2 pi, I also get 0. So 0 comes out here. For the next one, we have 1 against e to the ix. Same idea. E to the ix goes to e to the minus ix. And we just saw that that's going to be cosine x minus I sine x. The cosine and the sine are going to go to 0 when we integrate. So 0 comes out. Then, if we do e to the ix, e to the minus ix, okay, e to the minus ix becomes e to the ix, and then we get e to the 2ix. That is going to change by our second computation to cosine 2x plus I sine 2x. If we do each of these separately, we'll see that we get 0. So just do a u substitution with u equal to 2x. So our three functions are going to be mutually orthogonal. Now, we also want to see if they're unit vectors. So if I put 1 against 1, all we're doing here is integrating dx. And then we put in 2 pi and 0, take the difference. So that's just going to give me a 2 pi, but we're dividing by 2 pi, so I get a 1. It's going to be the same idea for the next two. The idea is when you take the conjugate, what happens is the thing you're going to integrate is just going to collapse to a 1, and then a 1 comes out. So I have an orthonormal set, and then for the span, it's going to be an orthonormal basis. One last thing to note, okay, by Euler's formula, we're to have that the span for B1 is equal to the span of B2. So what does that mean? Well, what we're trying to say here is, if you note, if I have e to the ix, I can write that in terms of cosines and sines, as long as I stay over the complex numbers, because I'll need to use that I. I could also write e to the minus ix in terms of cosine and sine. So the idea here is we're just kind of pushing around the vectors, okay? They're not going to produce anything that's outside the span of the other one. The other thing we still need to see is I can write sine and cosine in terms of e to the ix and e to the minus ix. And we'll do that on the next board. Finally, verify Parseval's identity for sine of x using B1. Using B2, or the inner product itself, we've seen that the length squared of sine of x is equal to 1/2. Because B1 puts us over the complex numbers, we need to make a slight change to Parseval's identity. Instead of sum of the squares of the c's, we use sum of the squares of the moduli of the c's. If I have a complex number, we get its moduli squared by taking the complex number multiplied by its complex conjugate. Now, the identity I'm going to use for sine of x, that's going to come from Euler's formula. So it's going to be given by 1 over 2I times e to the ix minus e to the minus ix. You take Euler's formula, substitute in for your e to the ix, your e to the minus ix, simplify. That's going to collapse down to a sine x. You have a similar identity for cosine x. That's going to be 1/2 e to the ix plus e to the minus ix. So once you know that, we have that B1 and B2 are going to have the same spans over the complex numbers. Now, because we can write sine x like this, we can put it in linear combination form over B1. So that's going to be 0 times 1 minus 1 over 2I e to the minus ix plus 1 over 2I e to the ix. Parseval's identity says we take the sum of the squares of the moduli. So what we're going to get, I'll have 0 squared, okay? The modulus of minus 1 over 2I is going to be 1/2. So that's going to go to 1/4. And then same idea for 1 over 2I, its modulus is 1/2. So that's going to go to 1/4 also. We take the sum, we get 1/2, and then that agrees with our previous two computations. Now, let's verify the coefficients in our linear combination. Here, we're going to use the formula Ci is equal to the inner product of your vector with Ei. Okay, C1, we're going to take sine of x against 1. So it's going to be the integral from 0 to 2 pi of sine of x. That's going to go to 0. Then for C2, take the inner product of sine x with e to the minus ix. Take the complex conjugate of e to the minus ix. That becomes e to the ix. And then we sub in using Euler's formula. So the e to the ix becomes cosine x plus I sine x. We have these two terms, so we treat them separately. The first term, you do the u substitution, u equals sine x. That's going to make your integral go to 0. Then for this term, we have sine squared x. So I'm going to use cosine 2x equals 1 minus 2 sine squared x. Isolate the sine squared. Then when we take the integral of this, what happens? This piece is going to go to 0. And then out of this piece, we're going to get a 1/2. So I'm going to have I over 2. Well, to move I to the denominator, the penalty is a minus 1. So C2 is going to be equal to minus 1 over 2i. Note, that agrees with our linear combination. So it's a coefficient of e to the minus ix. Then for C3, same exact computation here. Okay, we're going to have e to the ix in our second slot. So that becomes e to the minus ix. Using the Euler formula, we have cosine x minus I sine x. So the only change is going to be this minus sign here. So we just take C2, change by a minus sign. So we get 1 over 2i. Then you'll note that agrees with the linear combination. That's the coefficient of e to the ix.